Oh, that's why, because I wasn't in the show. So okay, yeah. So I'm learning production stuff as I kind of go along. That's why you couldn't. Yeah, that's why you couldn't. That's why we couldn't hear each other today. Neither one of us was at it. Because I'm looking, I'm like, are we supposed to be grayed out like that? And I'm like, why didn't I show up? So hey, there we go.
Oh yeah, hallelujah.
Right. So today is experiment day. Okay. Hence the goggles. Yes. Because, safety first. So the experiments we'll be doing today, we actually have several. These are just the box covers for these, but it's several different. Here, got my iPad in the way. There we go. So it's several different ones in this one. It's three in here and then two in this other one. And we're going to start with these because, colorful chemistry is always fun. So this is my little setup. So I actually have a cup of water here just to fill this beaker up with the stuff. There, our beaker. And then I actually have this extra little plate here because I want you to be able to see the colors side by side, and there's not enough room on this little tray for me to set them all side by side. Oops, that's my phone. So Male Science, they actually have like an app where you can follow along with the experiment. So this is the app. This is where they, tell you what your supplies, and then they walk you through it step by step with little video, stuff. So it's a very nice service to get. Um, it's about what 37 and some change a month. This is for the chemistry experiments. They have physics experiments too. I'm not sure how much that one is, and they vary by the age group that the experiments are suitable for. So I would definitely check out their website if you are interested in doing these experiments for yourself at home. And they provide all the safety stuff. So these goggles they sent in the initial kit. There's gloves and all of the sets. So there's there's usually two pairs of everything. So there's another set of goggles for your child, for at least one other child, and they have a bigger set for the adult. And then they send usually two sets of gloves, one or two sets of gloves for whoever's going to be handling the stuff to wear. So for the most part, like the dangerous stuff, I would suggest you probably wouldn't want your child to handle that themselves. So I'm assuming that's why they only put one pair of gloves in here. But safety first. So you always want to wear your gloves and your goggles when handling any type of liquids, fluids, and materials because you just never know. And most of the stuff is not like extremely harmful. Some of the acids can be quite corrosive, so that's important to protect yourself against. And pretty much all of the items are uh hold on, she wants more chocolate milk. Let me get her some more chocolate milk before I get started, because once I start touching this stuff. All right, we're back. Yeah, she already had a real bad tantrum earlier where she pretty much shattered all of the glassware that we have on the wine cabinet. So, yay, us. And now it says you pull out all of your materials. So, this is actually for a later experiment. So, it's this petri dish. So, we'll put this stuff to the side. And each of the experiments have their own experiment card in there that has a step-by-step walkthrough that you can read and look at. So not only do they have the one on your phone, so if you don't have your device available or you don't want to get it messy, that's fine. It's a written version of it as well. We'll be needing our spoon and our bottle opener, which is a paper clip. And then this one, where is this? Methylene blue sodium. That's for another experiment. And that's for the other experiment. So these are our reagents. So the reagents or reactants. So the stuff that's doing the moving. That little thingamabobber. Stir sticks. And then we'll get that out of the way. So it's always important that when you're doing experiments, wherever, if you're in a lab, if you're at home, you always want to keep your experiment area free and clear of stuff that doesn't need to be right there, because, you know, you want to mix stuff up. And normally in like regular labs, all of these cups will be labeled with what's going into them and all of that. But since it's just me and I don't have to worry about someone coming up behind me and grabbing something and using something or whatever and not knowing what it is, I don't have that problem. But if you might have that problem, you would definitely want to label your containers. So we have our spoon. So we're going to take the big part of the spoon. So one big spoon of our pH indicator, which is thymol blue. And as you can see, it's really darkened in this container, but if you, I don't know if you look, it looks blue. So the name thymol blue is because it's blue. And so it has a child protective cap on it. So that's always helpful. And then the paper clip for our bottle opener, we push the little, they have like a little waxy something in there that plugs it as well. So it keeps it pretty secure while shipping and you're not using it yet. So I can appreciate that. And then it has a very easy little drop top, and we're going to squeeze that in there. One big spoon of thymol blue into our beaker. And you see it's blue. It's very, very blue. So I'm going to actually set that on the edge there. And always recap your containers. If they have caps, recap them when you're done with it, like always. That's a hard learned lesson that I had to learn, because I spilled sulfuric acid and almost set the lab on fire one time. So, and then we're going to take our water and add it to here. So I'm going to put 250 mils in here, and I'm just going to pour the 50 mils in each of these cups. Okay. And as you know, you're going to notice that as I pour the water in, the color changes. You see? The color is changing. It is no longer blue. So this is our pH indicator. So water is actually not basic. It's not quite neutral. It's actually slightly acidic, because there are hydrogen ions, hydronium ions, which is H2O with an extra hydrogen ion attached to it. So it makes it H3O plus. And then there are H2O molecules, which are neutral. And then there are OH minus ions. So from that list, you can tell that there are more positively charged or acidic molecules and ions in the water solution than you know, neutral or basic. So it wouldn't necessarily register at a basic pH. So now we're going to start adding our solutions here. So the first one we're putting in is sodium hydrogen sulfate. So that's the the chemical formula for that. So Na is sodium, H is hydrogen, S is sulfur, and the O is oxygen. And there are four atoms of oxygen in this compound. So this is would be considered a solution because it's liquid. So yeah. Is that? Because I think I have pH indicator on my little paper clip, but we'll see. And then we use our bottle opener. And then we're going to put 1 drop in there. That's all it takes is 1 drop. Or is it 10? It's 10. The 0 was covered. Okay, 10. So it's 3, 7 more. Okay. I thought 1 was like a bit of a small amount. And next, we're going to do our citric acid. So I don't think they have the formula for that on here, but it's an interesting one. And I know you've heard of citric acid before because it's in citrus fruit. And that's actually what makes citrus fruit taste sour. So the more sour the fruit, the more citric acid it has in it. And usually also it might tend to have like a little bit less sugar. So put our citric acid in there. And then this next cup here is actually going to have a mixture of our citric acid, and we're going to open our sodium carbonate. This actually has the formula on here for 2 atoms of sodium with 1 atom of carbon and 3 atoms of oxygen. So these are actually, so the cation is the sodium and the anion is actually a combination of the carbon and oxygen. So that's what attracts those together. So the CO3 has a -1 charge. Well, a negative, yeah, that's it. A negative charge. There we go. Make sure it's enough in there. So we're going to put 5 drops of this. Did I open that? Squish that down some more. This one was, it's being difficult. Okay, there we go. No, that still didn't quite get in there. It's like, oh, okay, there we go. It ended up getting pulled back in place. Here we go. 1, 2, 3, 4, 5. Recap it. And our citric acid. 1, 2, 3, 4, 5. And these mixing together actually had a small reaction. So you see there's bubbles in there. That's the citric acid and the sodium carbonate reacting to each other, because sodium carbonate is basic, citric acid is acidic, and so they're going to have an acid-base reaction with each other that begins to kind of slightly neutralize each other. And there's some swapping of atoms and things like that that releases some some H plus, but also some OH minus. And then in this cup, so this one is, we're done with the citric acid now. It's just going to be our sodium hydrogen carbonate, which is baking soda. I got baking soda. So that, you see, that's the chemical formula for baking soda. If you ever wondered what that would look like. Is this? Oh, it's settled to the bottom. I gotta break it up. And we're gonna get our spoon and measure it. Is this okay? There we go. Yeah. That thymol blue was hanging on and it made a little pool, and I'm trying not to make a mess with it because I have to use the little part to measure this out for this cup. So we're going to do 1 small spoon of this. And when you measure stuff, always measure it over the container you're putting it in, because if you do end up going over, it's fine, but at least you will not have made a mess with some possibly harmful or toxic substances. Okay, there we go. And the baking soda is in. Let me put the cap back on it. And then in the 5th cup, it's just going to be our sodium carbonate. We're going to do 5 drops of that in here. All right, so we have everything set up now for this initial go around. So we have our pH indicator, which is now a kind of orangish, greenish color. I don't know that the water, this gives me I don't know, a little bit of pause because this is straight from the tap water. So this is not filtered water. So we usually drink filtered water. So I wonder if that will make a difference. I might do that after I finish this and see if the filtered water will have a different pH. All right, so we put in our 50 mils here. I have to pour with my left so I can see how much I'm pouring up out of here. Yay. Ambidextrous. Oh, it's off camera. Here, let me turn it so you can see. Ah, yeah, you see that color change. So that is an acidic pH that is making that. And so that's why most acids actually have acid in their name. I think like usually when they use the common name, that's the only time the acid part will kind of go away sometimes, and you won't know for sure if it's an acid or not. But yeah. And then this, so this is a pretty strong acid, which is why it's more of a reddish color. I'm not sure if you can see that color on there. For some reason, my color looks weird on my screen. Okay, and then now this is going to be mostly orange. Did I write down 200? Yep. And then this one's going to look yellow. Move that back so you can see it. So this is our solid baking soda. And that is green. Let's stir it up a little bit. And that's how you know you got something basic going on. And this is our last solution, which is blue, which is very, very blue. And it's actually probably more vibrant blue than the indicator, thymol blue. So this is above pH 10. This is about pH of 9. This is between pH 3 and pH 8. This is pH 2, and this is pH 1. So to give you a point of reference, carbonated acid has a pH of 1. So this would be, what less than 1 would look like. It's red. Carbonated acid. Your stomach acid would prompt an orange indicator. Cola. So if you like Pepsi, Coca-Cola, tea would also make the indicator turn yellow. And drinking water, Like I said, you see this, I wouldn't drink this water because it's like I said, it's direct from the tap. So like I said, I'm going to try it with my filter water, and then we'll see what we get. That's going to be fun to investigate on that one. And also seawater would be in this range. Thank you. Soaps. Soaps would be in your pH 9, and drain cleaner. We actually keep some, but yes, drain cleaner is basic. It's extremely basic, and what it does is it ends up essentially melting whatever is clogging your drain without making it burst into flame. So if you poured hydrochloric acid or sulfuric acid down your drain pipe, it might ignite some things in there with how it reacts with stuff, and also it could be very corrosive to the metal pipes, because metals tend to react very actively in acids. That's usually how you get metals to ionize and form oxides, and that's bad for your pipes when you need to use them. So that's why we don't pour acids down our drain to unclog them. And so this what's going on here is that when the citric acid, that's citric acid in there, right? No, the hmm, sodium hydrogen sulfate. So what ends up happening is you put the sodium hydrogen sulfate. This is a salt. So if you put your alkali earth metals with anything, it's going to be called a salt. So this is the salt form of sulfuric acid. Once it reacts with the water and the indicator. So the indicator is in here in a negative ionic state. It has a two negative state, ionic state. When you pour this water in with the sodium hydrogen sulfate, what happens is that the sodium hydrogen sulfate dissociates and it releases hydrogen ions, and then the sulfate ions interact with water, and it forces the water to break up into more ions so that more of the hydrogen is released. And then you have a very acidic solution. So in this one, citric acid is not, it doesn't ionize as well as sodium hydrogen sulfate does in water. So it has fewer hydrogen ions, free ions loose, to interact with the indicator. And so now you have a mixture of this bright red, which is the indicator binding with the acid in there, and a mixture of the unbound indicator, which has a kind of yellowish tint to it. So boom, red and yellow, you get orange. So in this yellow one, you actually have even less. So there's almost like no hydrogen loose in it. So it's barely binding with the indicator enough. So all of the indicator is converted to a not completely bound state, which is red. So there's no red in this. So you end up with just yellow. Then in this one, you are producing OH ions instead of hydrogen ions. And so what happens with the indicator is that now, because you have this yellowish color, because there are still some hydrogen in here, because I did put some citric acid in here. So there are still some hydrogen ions in here, but it's like way fewer. So now you have a combination of the one hydrogen binding to the indicator, making this yellow solution, and then also having no hydrogen bound to the indicator, which gives you some of this blue, and then combined you get green. And then this is no hydrogen present, just all OH, and so you end up with just pure indicator and you get blue. So that is the beauty of acid-base chemistry, and usually that is how we go through and find out how acidic things are, and it's all eyeballed unless you have an electrode pH indicator. So that's where it's like a little probe. It has a little glass ball with a metal filament in the middle that measures electron potential in the water. So the ions that I was mentioning in each of these cups, generate an electric potential, because ion movement is also electron movement. So based on the what the probe indicates in, I think sometimes measured in millivolts, then you can get a more accurate and precise indication of the pHs of solutions, as opposed to trying to eyeball it with a little indicator that has like red, orange, yellow, green, blue. How red is it? How orangish is it? You would have to guess. So to get a precise measurement, you would have to use an electrode. Now, oh, let me get that filtered water, because I definitely want to see that. All right, so this is my out of the filter water, and I have my thymol blue, and I'm just gonna put a drop in there and see what color we get. All right, so side by side. Oh my gosh, look at that. You see that? Oh, that's crazy. Who would have thought that filtered water would be that different? Like, it almost still looks clear. Like, I'm looking at it, but it's not, it's definitely not that. Here, maybe if I turn this light, y'all can see it better. That's still, this still looks almost clear. But yeah, that is crazy. Here, let me see if I can hold this closer. So this has a very light yellow tint, and this is like almost like dark greenish. So I don't know. That worries me a bit, but that's why we don't drink straight out the faucet water. So we're gonna dispose of these into, I'll put it in this beaker. We're just gonna pour all the stuff in there. That's how acidic that is. It turned the whole thing. You saw how dark it was, turned the whole thing orange. That's how acidic that one little cup of stuff is. Okay, and we're gonna pour this out. Dispose of this. Okay. Since we're using really small amounts of this stuff, um, it's pretty much safe to just rinse down the sink. So I just flushed it with extra water to dilute it, and it's gone. So I'm gonna put this stuff, these reagents, back in their bag to get them out the way. And then now we're on to our acidic patterns. So this one's going to be kind of fun too. Acid-based chemistry was always like fun to do, but like for me, it was the calculations and the technical stuff that always like tripped me up. But I love watching the color changes. The titration sometimes were kind of boring. So titration is just very, very slowly adding acid to a basic solution. So you see how like the color like immediately changed from that darkish greenish blue to like that bright orange. That's what titration slows down. So we want to see the exact point where the water goes from like that dark greenish bluish color to like a full even orange color or whatever that pH would be. And so we tend to use a different indicator because we don't want our solution that we're titrating into to have color. So it tends to be something, an indicator that is not colored, so not thymol blue. We usually use phenolphthalein for that because phenolphthalein is only pink at acidic pHs. And so right when you hit what they call a titration point, which is the point that the solution moves from basic to acidic, is going to turn to like a very bright pink. So a light pink. So the lighter the pink you can get, the closer you are to that exact titration point. And then you measure how much of the acid it took to, or usually it's the base. Yeah. I got it mixed. I might have had it mixed up. I have to look it up and get back to y'all. It's been like 15 years since I've done that, so bear with me. But you measure how much of the solution it took to create that change, and that's how you. And then it's like some calculations that you do, and then boom, you can find out how strong the acid or base is that you were titrating. Fun, huh? Okay, so we got our stir. So we're going to need this to stir. And we're actually going to use a different spoon. So we stick that spoon with that stuff because we don't want to cross-contaminate stuff. So our bottle opener, our Petri dish. And then, is this the right one? No, this is for the other one. All right. So this is the one. So we're going to open our Petri dish. Ooh. All right. So, and sometimes these experiments use some of the same. So that one, we just use that in the other one. So I think I'll actually use that one from the other one. Because I don't really feel like having to open this one. And plus, boom, it's right on top. Yay me. So it's already open. Want to put 3 drops of this in here. Okay. And then we're going to pour some water in. Here, I'm actually going to pour some in this beaker because this tall cup is going to splash. We're going to pour some water in there. Make sure it coats the whole bottom. I'll pour a little bit more in there, about halfway full. And then we have our indicator, which is also thymol blue for this experiment, but we're going to put the drops directly in the Petri dish. So 10 drops. 2, 3, 4, 6, 10. Move y'all closer because it's like this light is washing everything out. There we go. You should be able to see that better. Okay. Then we take our stir, we stir it up. Stir it up. Wash it all blue out. Hold up. Okay, so make sure the indicator is evenly distributed and mixed in. And then we're going to take our sodium hydrogen sulfate, which was also in the other kit, because like I said, I'm trying to minimize how many times I got to fight with that little bottle opener, also known as a paper clip. This works. Haha. So we're going to put 5 to 7 drops of this in a couple of different places. So I don't know if you can see these colors already kind of starting to change. So and then we're going to take this. You see the colors popping up? Oh, so what's happening is when I drag this stick through there, it pulls the sodium hydrogen sulfate around in the water. And like I said, once it does that, the sodium hydrogen sulfate interacts with the water and creates sulfuric acid. And that's those little, the yellow and orange areas are the highest concentrations of those ionic reactions happening that's pulling the hydrogen out of the water. And then the indicator is mixing with that. And then the blue part is where that's not happening. So where the, what else do we put in here? Our sodium carbonate. So you spin it around, you see that blue pops back up again. And more orange and more yellow. So now the hydrogen sulfate is completely acidic.
Oh. I just had to pause real quick to say that's so pretty.
I know, that's why I was so excited about these experiments. I was like, oh, colors.
Yeah, that is so pretty.
And so the way we can take it back though, we can bring it on back. So now everything is yellow because it's all equilibrated down to an acidic solution because of our very, very strong acid that's formed in there, which is sulfuric acid. But we can get some basic swirls going by adding 5 to 7 drops of our basic solution. And so now you can see that blue coming back in there, and then we swirl that around and it neutralizes the sulfuric acid. And so it pulls all of those hydrogen ions back out of solution and it turns the indicator back blue. And then we can get back all the way back to a solid blue state. So that's how acid-base chemistry is super cool. And yeah, yes, I'm finna do it again. You already know I'm finna do this again. Back to the bring it back. Oh, bring it back. Oh, bring it back. Oh. Oh, maybe I didn't put enough acid in there. Here, let me just. It's some swirls of yellow. I think it's starting to. Oh, there it is. There it is. You see it lightening up. It's doing it all on its own now. And so I could pull it through there, and then that will concentrate. Ooh. Shut the front and the back door. We did stuff like this, just not like this particular like fun swirly color type situation. Give me those, give me those, give me those. Oh no. She grabbed the old cups. So this experiment is now complete. So I'm actually going to just pour this in one of these old cups that we used. And now we're going to do our colorful milk chemistry. I'm not sure why they gave me that one, but we'll see. We shall see. Oh, I guess these are extras, right? Because that's needed in both the experiments. I can see how that could be a thing. Yeah. Because this is the one this is the one I didn't open. Trying to keep everything straight and together. And this, we do need this one for this experiment. And so this one is called color changing milk, but milk is expensive, so I'm going to use this white background. So really the milk is not pertinent to this experiment. It's literally just to create a white background for you to see all the colors move on. And so that's all we need it for. So wipe this out because we're actually going to need this same little petri dish. Okay. So starting from fresh, we have our soup. All right. So I'm going to pour some water in here. Make sure it covers the whole bottom of the dish. Then we're going to do, so we have, so this is just a regular food coloring. So yeah, food coloring. This is another indicator that we tend to use, methylene blue. And this one. And this is AOSIN, where we at? Which is another indicator. So we're actually going to need to freshly open all of these. Oh, that's okay. That's very red. And we're going to just do drop. And so they behave kind of well. I think if I use milk, they probably wouldn't spread out so much, but it's fine because by the time we get to what we're doing in this, oops, we shall see. Okay, and now the yellow. And then we put our soap. Oh, that. Oh, I hope I didn't poke the hole in the wrong. Okay, there we go. That's her favorite song. She had to run over here. And so now we're just putting the soap on the tip of the Q-tip. You see it swirling, and then we're just gonna boop. Oh, did you see that? I wish we could do like a slow motion thing because that would be like so cool. And so what's happening here, so I'll probably have to use more soap on the other end. So what happens is when you have the soap on the end, the soap gets drawn into the water and then it creates a film over it. And so that's what made the color shoot out away from the Q-tip. And so now here I'm going to do it on the other end too, just in case you missed it. So we're going to do it on the other end as well. So oh, the color ended up sinking down under the water. So now I believe it's all the way covered. The whole surface is covered with the soap because now the colors are under and they're not being pushed away. So if we drop the soap directly into it, let's see what happens. And it's actually still kind of pulling it. You see how it's pulling it that way? So I'm actually gonna do this one again, and I'm gonna try it with actual milk to see what the difference is. Oh, the beauty of experimentation. Take your time. All right, so I went and got some milk, and we're gonna get to see the difference between how the water and the milk go. Ah, pop that bubble. Ah, see, so the coloring does like stay more in place with the milk. I would think it has something to do with the fats in the milk, so it's not so soluble like how water is. Water will pretty much dissolve almost anything in it, and then these colorants just sink to the bottom of the petri dish in the water. So okay, so that's how they're looking. And then we have another Q-tip here. I'm gonna put the soap on the Q-tip. Woo! Oh, did you see how that? Oh, shut the front and the back door. That was very quick. Oh, and it still like moves it. Oh, ooh, yep. And so this is essentially what makes soap. So soap are surfactants, and what surfactants do is they separate molecules and atoms and things from each other, and that's what causes the repulsion force. This is so much fun, and it's really pretty. So that's that, and then let's see what it looks like to just drop the soap in there. And so it's actually the soap drops that's in there, they're spreading out across the surface from their spot, and they're forcing like little circles of the stuff around it. That's so cool. And we actually put there's actually surfactants or soaps and things in things like paint. When I worked in a paint manufacturing facility, we put things like surfactants in the paint because of that whole situation. So when you're mixing paint, all types of stuff go into it, and the surfactants actually help keep things that don't necessarily mesh well from binding too quickly when it's mixing. And then we also mixed different things in different stages. Uh, so the main body of the paint was mixed first, and then all the soaps, the biocide, and all the other things would go into a whole nother tank. And then the main, like what we call the grind, so all of the sand and gravel. Well, it wasn't sand and gravel, but if you think sand and gravel mixed with water, that's essentially what was being pumped into the tank, which makes the paint. And so yeah, that was so much fun. And now we're on to our bottle. Let me get the beaker stuff. Push this off to the side. Put these back in the bags. And so these two experiments are pretty quick, but it's, I would say that probably like the cool thing about it is that one of the reagents that's a part of this experiment that we're about to do is something that we all use and we don't necessarily know or remember that we use it until we don't have it. And that's kind of essentially what's happening with this experiment that we'll be doing next. Is this the one we're doing? Was it burn? Yeah, we're going to do that. Got the soap out. Put these away. We don't need these. We're moving on to our next experiment box. I'll pack these up properly in a minute. I just need these out the way. Okay. Spoons back in their spot. Okay. So now we're on to, so the main thing with this one is oxygen. So this one was colorful chemistry. This one that we're doing now is oxygen. So in case you didn't know the answer to the riddle I gave you earlier, it's oxygen. All right, so yeah, that's the one we're not doing yet. What's this? Yeah, here we go. Glucose. This one also has a set of gloves that I don't need because I already have on gloves from the other experiment. And I have my rubber stopper because we're going to need that. Now this says warm water. Let me see. I don't think this. Yeah, I have to go and get some warm water real quick. So I just turned the water on for a bit and let it get hot. And so now we're gonna just fill the flask about a quarter. Okay. And then we're gonna add, where's the glucose? So that's, in case we mess up, they gave us another bottle because we'll actually need this whole bottle. And because we need the whole bottle, I'm just taking the stopper out and I'm just gonna pour it in there because I just feel like that's a waste of time trying to poke through that, and all I'm gonna do is add the whole bottle. And then we have our indicator here, which is methylene blue. This I will have to stab open. Let's see, they gave me a fresh paper clip. Here we go. You would think this wouldn't be this hard to open. Okay. And then take this out because we got a dropper. 5 drops. That didn't open it. There we go. Okay. 1, 2, 3, 4. And where's our spoons? Yeah, this is the clean one, I believe. Yep. And then we're going to do 3 big spoons of sodium hydroxide. So if you were watching closely in the first experiment with the acids and bases, you know that methylene blue is also a pH indicator. It's not thymol blue. As you can see, this gives a much more vibrant blue, and it also is blue with stuff in it. So methylene blue, the only color you're going to get from it is blue. With thymol blue, you get different colors based on the pH. So that's the main difference there. So they gave us a solution. Sometimes they'll send solid sodium hydroxide, which just looks like little, like, I don't know, because it's not quite like salt crystals, but they're like whiter, I guess, like baking soda, but not crumbly like baking soda. So we're adding 3 big spoons of this. Oops. It said big spoon. Okay. Put a cap back on that. Now, close that up. Now we're going to put our cork on there and swirl it around. And you see it's actually getting bluer. So it's much bluer than when it started. So that means it's very basic at this point. And then we're just going to watch it. And so what's happening, oh, get this card in the way. So what's happening with this one is that you have glucose, which is a reductant. So a reductant is a reducing agent that loses electrons. So the methylene blue indicator is taking electrons from the reductant, which is glucose, which makes the solution blue. So when methylene blue, it has excess electrons, it's blue. So that's why it's usually a base indicator. So it indicates, so OH minus is essentially electrons moving because OH has extra electrons on it. So anything that accepts OH minus is basically accepting electrons. So the methylene blue is getting those electrons from the glucose in the water. And what happens is that a powerful oxidant comes along named oxygen. Oxygen ends up taking those electrons from the methylene blue and it makes it blue again. So while this is reacting in the water, did I shake that up good? Because the glucose has to dissolve all the way in here, or it's not gonna do its thing. So as the methylene blue takes those electrons from the glucose, it gets neutralized and happy, and it should be clear. So it said sit for 1 to 6 minutes. And then once it gets clear again, what happens was what we're going to end up doing is we're going to shake the flask again, and then the oxygen that's in this space above the solution is going to take the electrons from the methylene blue and make it blue again. And then that we can just keep doing that over and over again, turning it blue back and forth, and it can be a yay or nay. So let me see. Will I need this same? Oh, my mom made it back. It still looks very blue on the camera, but me looking at it directly, I can tell it's getting lighter. It's almost like back to where it started before I added the sodium hydroxide. So we'll get where we at with time. Okay, we got enough time to do this last experiment. You know I like burning stuff. So this last one we get to burn some stuff. So no, I like burning stuff. Oh, and this is cool too. So she put her hat on her. This is too cute. Now all she needs is a terrible Cockney accent and a newspaper stand, and she'll be right on the money. So this is our manganese oxide for our next experiment. I don't know if you can hear that, but it's solid. And manganese is one of the transition metals that we'll be talking about as well. So don't worry, we're going to get to it. And it's super important for stuff in your body as well. So, yes, it is a metal, but it's also important, very important for life and all kinds of things that go on inside your body. Let me see. Has it been like 6 or 7 minutes? Let me see if they'll say what to do if it's not changing back fast enough. Let me see. No, I didn't. Oh, warm water. So the water I used probably wasn't hot enough. So here, we'll do this. You watching the flash for mommy. She watching me carry that flash the whole way. So, hey Marley King. You have to use that shaker sound on the beat. Okay, I know. Like, I got you. Don't worry, I got you. I'm gonna just pop in. So as you can see, now it's completely clear. So all I did was run it under hot water until it turned clear, and it actually went from that blue that you saw to a lighter blue to clear. And so all the hot water does is just it catalyzed the reaction. So you see, even when I bumped it, that little bit of blue. Oh no, the cork popped out. But yeah, that's funny because I guess it's gas and heated up the oxygen gas above it, and now it's pushing the cork out. So just like a little shake will turn it back blue because there's oxygen that pulls those electrons off of the methylene blue in there, and it turns it back blue. And you see it swirling and swirling, and it's getting back clear again and getting back clear again, and it's back clear. And give it another shake. And so when every time you shake it, it makes the methylene blue interact with the oxygen above it and pull those electrons back off of it and turns it back blue. And if you let it sit long enough, the oxygen is a very strong oxidizer. It'll be like, hey, give me my electrons back. And it snatches those electrons back off of it, and you see it starting to turn clear again. Ooh. This is exactly why I was a chemistry major. Because of stuff like that. So super fun. And now we're gonna light some stuff on fire. Okay. I actually have my little lighter. They say use matches, but I don't have any. I don't have any matches. So we're gonna dump this. Let me get my lighter. Okay, so now, so it says 1 ampule, so I'm assuming it's this whole thing right here. Is this open or do I gotta cut it? I think I gotta cut it. Some scissors too. It didn't even say I needed scissors. All right, so snip the end off. So we can. Whoop. And this is hydrogen peroxide. So let me see what's the other one in here, because you probably could do this. That goes with that. Yeah. Oh yeah, no. You wouldn't just have manganese just you wouldn't just have some manganese oxide just hanging around in your house. But I'm like, if you got some peroxide, we definitely got that. But this is 3% solution. I think most of the stuff that you like would have in your cabinet is like 9%. That sounds right. Because isopropyl is like 70%. And I think if the hydrogen peroxide was any more concentrated, it would burn like a lot. And so now we're going to take one whole bottle of this, of our manganese oxide. So I actually have to take my gloves off because I got to light this. So we pour this in. I really should have kept my gloves on to pour it in there, but I want it to be ready so I could light this without accidentally catching like the glove on fire, because you don't want to catch your glove on fire with, it on your hand, because it'll melt. So that's a whole nother. I'm standing right under this fan and it is not letting this. Okay. All right. So we light the splint, we let it burn some, we blow it out. I don't know if you can see that. Let me make sure. Yeah. Because we want the splint to have red hot embers, but no flame. So you see, whoop, now there's no flame, it's red hot. Boom! And that's pure oxygen, baby. Right there. So what's happening here is that it's funny because when the closer I get to where the oxygen is coming from. So now it's getting filled up with carbon dioxide from the smoke. But you see it's still lit. I could probably get it to light back up because the reaction is still going on in there with the manganese oxide and the peroxide. So it's just a simple replacement reaction, single replacement reaction. I don't know if you can see that, like getting brighter. So it's giving off pure oxygen in this reaction. And when the splint, even though the splint is not in flame, it's just red ember, the oxygen reignites it. So here we'll stir this up. So I think this is it's a little bit of manganese on the side. Rinse it down in there. Yeah. And so all we did was just catch that oxygen that was coming off of there. So that was fun. And so what we have here is our peroxide is the separation of it into oxygen, which is O2, pure oxygen, and water is catalyzed by manganese oxide. So manganese oxide is happy. Transition metals form oxides very readily, and so they're happy once they're in an oxide. And there's other stuff, usually like acids and things that you have to do to separate them. And so, in this case, it's acting as a catalyst to move along the reaction of peroxide, because peroxide spontaneously goes to water and oxygen. So that's why if I don't know if you've ever left a peroxide bottle open, it's no longer active. Like if you end up trying to use it on like a cut or something, it doesn't burn. Like, hey, this didn't burn. Like, yeah, because it's water now. So that is a spontaneous reaction that will occur over time. But the manganese oxide was a catalyst in this case to make it produce a ton of oxygen in a very small period of time. And so when you lit the splint and it had like a little bit of ember on there, what happens is that the wood was still on fire, it was still burning, but it just wasn't catching the other oxygen and particles in the air on fire. So that's usually when you see the flames. Those flames are actually more that heat catching on to things around it. And so the oxygen readily reacts with organic compounds in the wood, and the heat and light are emitted during this reaction. So only a small amount of the air that we breathe is oxygen. So in this case, with it being pure oxygen, it like ramped that up a whole lot more. And so that's what is called a heat stroke. So yeah, some flammable particles leave the splint, and then they actually increase the size of the flame as though that oxygen comes in there. So that was our fun day, experiment day. It was our acid-base chemistry. We had some just some nice, colorful chemistry too. So not all of it was acid-based. So a lot of acid-based chemistry, and we also had fun with oxygen and setting stuff on fire. So next week we'll be getting back into our transition metals. So we will be starting off with manganese, which is what we finished off with today. And as you can see, one of its main things that it loves to do is catalyze reactions. So this is exactly what it does for us in our bodies, is it catalyzes some very important reactions. I will be talking about those next week, and a few of the other transition metals that are kind of grouped around it. And we have about 2 or 3 more weeks of transition metals, and then I think we'll get into some cell biology and genetics, because I don't know, it's fun. Cell biology and genetics is fun. Like for me, it is super nerd. So that being said, definitely make sure you tune in to our RockTrue Beat show, which is right after this. Yes, thank you everybody for tuning in. I love the curiosity, because I'm super curious about science, all that stuff, technology. I dibble dabble with my laptop and stuff sometimes when it needs fixing, because it's expensive to take it to the shop sometimes. So definitely come here, get your science fix, get your info fix. If you have any questions, do not hesitate to ask them, because I love answering questions. If I don't know the answer off the top of my head, I will absolutely look it up and get back to y'all with it in our next show, like I usually try and do. And following up right behind us in 30 minutes is RockTrue Beats, which always has somehow there's always some science up in there too that put the meat on your brain. And I believe we have a guest tonight. So tune in and rock truth with us, all right? Or nothing at all.